The last speaker will be Dr. from Yeah.
So let me then, on behalf of the Nuclear and Particle Physics Group, welcome you to RISE. The Nuclear and Particle Physics Group at RISE, there's about 8 people that I'd like to point you out to. There's Marge Cochran, Carl Eklund, Jay Roberts, Paul Patney, myself, Paul Stevenson, Bill Loeb, and Pablo Yepes. Marge, Jay, Paul, and Paul Stevenson, or both Pauls, are professor. Carl and I are assistant professors in the group, and Bill Loeb and Pablo Yepes are senior faculty fellows at the group. And so the activities in our group are as follows. We work on both high energy experiments as well as nuclear physics experiments, although these nuclear physics experiments by now are at an energy regime that is, that we rather refer to them as these ultra-relativistic heavy ion physics. But so on the experimental high energy particle physics, there are two things we're involved in. There's a D0 experiment at Fermilab near Chicago. That's where Marge Cochran works on most of the time. We are heavily involved in the CMS experiment at CERN, at CERN's LHC, that CERN LHC is running right now, although they're doing testing. But so that's where Carl Eklund and Paul and Jay are involved in. Then in the experimental ultra-relativistic heavy ion physics, we're mostly involved in the STAR experiment at another national lab, namely the Brookhaven National Lab on Long Island. There's myself, Bill Loeb, and Pablo Yepes who have been working on that, as well as 3 graduate students. CMS is a detector that actually not only is designed to deal with the proton-proton collisions that CERN's LHC is providing right now, but towards the end of this year, the same accelerator will actually accelerate lead ions. So that brings us back again to ultra-relativistic heavy ion collisions, and clearly I have a very strong interest in that, so we're definitely interested in using the CMS detector for measuring collisions between heavy ions at very, very high energies. There's Paul Stevenson. He's our theoretician. He was on theoretical particle physics. We also have, since a few years, Pablo Yepes working on particle physics techniques applied to medicine, and I'll get to that quickly in the next step. One of the things that I can say about what is most some commonality in the work that we actually, let's put it like this: we have 3 accelerators that are running. Actually, 2 accelerators that are running right now. And one thing that we all have in common is that both CMS at LHC and STAR at Brookhaven, or rather the RIC accelerator and the LHC accelerator, have been sued by people who thought that we were about to destroy the world by doing so. So just to show you where these evil machines are located, what we're doing in particle physics, we're looking at the fundamental components of matter and how they interact. And for that, we need really the highest energy to actually be able to probe these smallest of details of the matter. Like I said, there's for particle physics, there are 2 accelerators. One is at Fermilab's Tevatron, and the other one is CERN's LHC. Here's an aerial picture of that one. Interesting enough, both are closely located to Lake Geneva. There's a Lake Geneva next to Chicago, and as you all know, there's Lake Geneva next to Geneva. So there's a lot of, like I said, like I said, RISE works on the experiments, on both experiments, and here this is particle physics, so main focus here is to look for new particles and forces, to look for new symmetries and extra dimensions. And especially with the LHC coming up, the search for the Higgs boson and electroweak symmetry breaking is very much on the agenda. The D0 experiment is an ongoing experiment. It's the top quark discovery. You might have heard of the top quark being sort of like a 6th quark that people have been looking for. Top quark discovery is something that happened in D0. RISE contributions to that experiment have been not only in the physics analysis, but also, and that you see with the other experiments as well, in various contributions to the hardware, trigger electronics, the very relevant electronics that actually allows you to select what would be the most interesting event to keep, which, if you're looking for a top quark, is pretty important that you have that very well under control. RISE contributed to that. There's a central fiber tracker. What that means is just in the center heart you have a piece of equipment, a detector that allows you to very carefully track the particles that come out of these collisions. Luminosity measurements, important to actually get an idea about how often particular processes happen, important input to your theoretical models. D0 experiment up to LHC coming online had the highest energy data available, but it had the opportunity to run for a long time, so it has a lot of data, so it can actually already do various searches or actually look at limiting particular ranges for instance, where one should look for the Higgs boson. Data has been collected throughout until this year. There are 2 graduates working on that, and although it says here opportunities for new students, I have to say that we're right now not that much in a position to take students. But you're absolutely welcome to talk to Marge Cochran about this. The CMS experiment, here is an exploded view. Exploded is probably not the word that's most appropriate after we had a little bit of an incident in LHC in 2008, but there you have it. It's a very impressive machinery. I've worked on that for about 4 years. It's definitely, as you can see from this little fellow here, it is a very impressive piece of equipment. It has more iron in it than the Eiffel Tower has, and that is in a very compact way, as you can see from the title. It's only like 15 by 20 meters. That's not much for an Eiffel Tower worth of steel. This is big physics. There's more than 2,000 physicists involved with this particular experiment. There are other experiments, Atlas being the other one, which from the name we already can tell is even a large experiment. There are more than 3,000 physicists working on that one. Big physics. There's some great advantages from that, and I'll get to that in a second. This is, if you hadn't already gone through, this is at the Large Hadron Collider. We've seen first collisions. Actually, we've seen some in 2008. Those aren't really collisions, but they were the first test, and then something blew up. 2009, we had actually really first collisions, and things are right now, people are bringing machinery back from a shutdown and are planning to have a very long run throughout this year. So a lot of data will be collected actually in this particular year. You're absolutely welcome to talk to Carl Eklund and Paul Patley about what's happening there. Our contributions are, and this is where Carl Eklund mostly has been focusing on the pixel detector. Again, a tracking device that allows you to carefully see the particles come out of and follow their tracks through the detector. It's like I said, it's a really impressive piece of machinery. It's able to provide you with 40 million 3D pictures per second, and do that with a 66 million pixel accuracy. Resolution. I mean that is that's a nice piece of digital photography setup that you have there. Obviously, there's the data acquisition, which is kind of impressive if you deal with that amount of data. There's the end-cap muon detectors. The end-cap, these are the guys that are on this side, and on the other side, these are muon detectors. The RISE group has contributed quite substantially to those. Again, trigger electronics that allow you to select those muons that are interesting to look, for instance, for a Higgs boson. We've worked very hard in the last in the last 4 or 5 years in getting these massive detectors commissioned, and the physics interest. I mean, there's an enormous amount of fantastic topics. First off, looking at just the W and Z boson production and couplings, but obviously looking for new particles is one of the main goals that we want to get with CMS for particle physics.